So we saw that in the interaction picture, the operators satisfy the same equation as in the free quantum field theory case, but the field, but the states or the time evolution operator satisfies a more complicated equation. And it looks something like the Schrodinger equation. And that equation is I del U t comma t0 del t is equal to H interaction I t U of t comma t0. Now for notational simplicity, I will just write H interaction I as H. Let's call it HI. So this is our notation for the interaction Hamiltonian in the interaction picture. Now this equation is different from what we call the Schrodinger equation. So the Schrodinger equation is so here in the Schrodinger equation, we have the total Hamiltonian. So what are the differences between these two equations? Let's just first number this equation. We call this equation number 1 and this equation number 2. And there's some important differences. Number 1, the Hamiltonian in equation 2 has the total Hamiltonian, whereas the Hamiltonian in equation 1 is the interaction Hamiltonian in the interaction picture. The other important difference is that if the system is isolated, then in equation 2, the total Hamiltonian H is time independent. Say for isolated systems. Whereas in equation 1, H interaction is a time-dependent Hamiltonian. And not only that, because it's time-dependent, it may not, or it does not in general even commute with itself at different times. So because of the time independence of the Hamiltonian in equation 2, the formal solution to the Schrodinger equation is given by the time evolution operator, which has a very simple form. It's just the exponential of minus I h t minus t0. But because there's a time dependence of the Hamiltonian in equation 1, we cannot integrate this equation that easily with respect to time. So the Dyson series is a formal solution to this problem. So Dyson was able to figure out a perturbative solution to this equation. And of course, perturbative means that the lambda, the coupling constant, is small. As we shall see in the future, there is some caveat, but of course, if lambda is big, any perturbative solution, any series solution is not going to be possible. So let's see how we can develop the Dyson series. So let me just copy this equation and bring it down here again. So first we do is that we integrate this equation. A formal integration means that if I take u, t0, that's going to be given by minus 1 minus I, the integral from t0 to t of the interacting Hamiltonian like so. Here the first term, the one term, is there so that in the case when t goes to t0, this just becomes the identity operator, because in that case, the integral here would be from t0 to t0, so this will contribute 0. So this is the formal solution, but of course this is no solution because u appears on both sides. So we can solve this equation perturbatively, or we can solve this equation iteratively. So an iterative solution would mean that we get u t0 is going to be 1 minus I. The first term will be t0 t dt prime. And here what we'll do is that in this place, we will just substitute this whole equation again. And we shall keep on doing it. So the first term becomes hi t prime. And then the second term becomes minus I squared. Now there'll be two integrals. And the first integral will be from t0 to t, and we call that the integration variable, say dt prime. But inside, when we replace the u, we'll get another integral, which will be from t0. Now it'll go up to t prime. And this integration variable will be dt double prime. And there will be two factors of h. One will have h dependence, t prime dependence. The second factor will have t double prime dependence. And then the term after that will be minus I cubed, and then we'll have two factors of time integral with respect to dt prime, dt double prime, and dt triple prime. And the first one will have a limit from t0 to t. The second one will have limit from t0 to t prime. The third one will have limit from t0 to t double prime. And inside the integral, there will be three factors of h. The first one will be hit prime. The second one, hit double prime. The third one, hit triple prime. And so on and so forth. And they will have an infinite number of terms like this. Now note that in the second order term, like in this term, the second variable t double prime, goes from t0 to t prime, whereas t prime goes from t0 to t, and therefore t prime, so t double prime is less than t prime, and t prime itself is less than t, and all of these times are greater than t0. So what we can show is that, what we've seen is that first we can look at, so we forgot to mention this term. In this term, of course, t prime will be between t0 and t. So we have that t prime is greater than t0, but less than t in the first order term. But in the second order term, we see that t0 is less than t double prime, and t double prime is less than t single prime, and that is less than t. In other words, if I look at the t dependence of these h, we find that they are always in time ordered. So the h here is in the future of the h here, and the h here is in the future of the h here, and this is in future of the h here. In other words, all these terms are automatically time ordered by the way that we have solved the equation iteratively. So we can write our time evolution operator as 1 minus I. Of course, in the first term, there's only one operator, so we don't have to introduce any time ordering here. So this is, and the second term we can just write, at this point, this is redundancy because it's already time ordered, but I'm just writing it, the time ordering operator, just to, make things clearer. So this goes from T0 to T, and here we have D of T prime, and here this goes from T prime to T double prime, T0 to T single prime, and this is D double prime, and here we have H I of T prime, H I of T double prime, and then we have similarly the third order term. Now, if I look at the second order term, and let me just, draw a graph. So on the y-axis, I'm drawing t double prime, and here I'm drawing t prime. Because it's time ordered over here, we see that t double prime is always less than t prime. So if I draw through this graph the line where t prime is equal to t double prime, and suppose this is, say, t0, and this is, say, t, and this is also t, then what we can show is that the integral covers this part of the domain of integration. So in this part of the domain of integration, t prime is greater than t double prime. If we were to include this part of the domain of integration, then in that case, t double prime would be greater than t. So what we can do is that we can then rewrite this equation such that it now covers the whole domain, but we can make sure that these Hamiltonians are time ordered because we don't have to worry about this because we've already included the time ordered operator. So when we extend the integral from t0 to, say, t, then of course, this Hamiltonian would be in the future of this Hamiltonian. So this will have to be time ordered, so it'll come over this side, but that's taken care of by this. So we can write the second term as minus I squared, and because we're integrating over double the domain, we have to divide by 2, and we write the 2 by factorial of 2, and then so the integral now goes from t0 to t, t0 to t, and here we just so here we have d of t prime, d of t double prime, and then here we have time ordering of h I of t prime and h I of t double prime. Similarly, we can show that for the nth order term, we can rewrite the nth order term in the following way. So what's the nth order term? It'll have minus I to the power n, and then we'll have n number of integrals dt1, say dt2, dot, say dtn, and all the integrals will go from t0 up to, the first integral will go up to t, the second integral will go up to t1, the third will go up to t2, and the nth will go up to t n minus 1. And then we will have Hamiltonian hi, which depends on t1, hi, which depends on t2, dot, 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 hi, which depends on tn. But we can rewrite all of this, introducing the time ordering. And if I do this, and I can change the limits of the integral to go from t0 to t, but then I will have to divide it by factorial of n, and then this goes from t0 to t, dt1. All the integrals now go from t0 to t. But now the price we have to pay is that we have to introduce the time ordering here, because it is not, these integrals are not automatically time ordered like the previous line. Right. So now we can write a formal solution to the Schrodinger equation or Schrodinger-like equation. So u of t, t0 is going to be given by an infinite series where n goes from 0 to infinity, and each term has the form minus I to the power n divided by factorial of n, and then n factors of integral over time. And then we have time-ordered n factors of Hamiltonian, which depend on t1, t2, up to, say, tn. And this, we can write this as a formal series or a formal powers exponential, which is the time-ordered exponential of exponential e to the power minus I. The integral goes from 0 to t, and then we have d of, say, t prime, h of I of t prime. So u of t by t0. So this is what is called the Dyson series. It is the formal solution to the equation, evolution equation in the interaction picture. And for our case, we can rewrite this as, we can of course so we can rewrite this as an integral over all space-time, and basically we will have exponential, and here instead of integral over just t, we can have an integral over d4x, and here we will have h, the Hamiltonian density, and we can also express this as an integral with the sign change, so it's plus I d4 of x prime. Here we'll have the Lagrangian density. Okay, and we can also drop the primes. Yeah, so this is the formal solution to the evolution equation, and this is known as the Dyson series. And this is one of the most important results in theoretical physics and applied mathematics.